Hello, everyone. I will start with a short introduction. I'm Cornel. I'm a software engineer, and I work in the data infra team for about 3 years. Spandana, if you can tell some things about yourself.
Sure. Hi, I'm Spandana. I have been with Crowdstrike for 3 years. I also work in the data platform team, and we work on the query ingestion and supporting analytical query platform downstream.
And with that, let's go to the agenda. In the introduction, we have some context data. I mean, who's Crowdstrike and what exactly are we doing? I mean, because this is kind of related to the data lake that we are building. After that, we'll show you the previous architecture based on Hive, the road of moving from Hive to Iceberg, the main components, which is ingestion, maintenance, query, and performance, our plans for future and our challenges, and probably you'll see also some of our mistakes. And at the end, in the last 10 minutes, is a Q&A session. If we are not able to answer to everything, we have our contact emails on the last slide, so feel free to send us emails and we'll try to reply to everything. Okay, so as I told you, just a couple of things about Crowdstrike. Our motto is we stop breaches. Who we are a cybersecurity company, and right now we are considered leader in endpoint security. We grew a lot during the last years. I mean, as you can see, I wrote we are producing right now about 3 trillion events daily. When I joined almost 3 years ago, we only had 1 trillion, which is good. At the same time, it has a lot of engineering challenges. What are we doing? I mean, what are we doing as related to our data lake? We have a bunch of agents, we call them also sensors, which are running in user or kernel mode on our customers' machines. And on the server side, on the cloud, we have a proprietary thread graph system. As I told you, we have a lot of customers, so a lot of machines which are sending these events. That's why we have this big number. And our team purpose, data infra, is to collect all this data, so all the 3 trillion events and other events produced by different systems. Some of them are internal Crowdstrike system. In other cases, we put together data from third-party systems. We put them together, and we have to make this data available for both internal and external customers. External customers means the customers that need all the data collected also in their system, of course, with a lot of enrichments, partitioning, stuff like that. And internal customers, probably the most common one in all the companies is the data science team. Right now, I mean, the current status, we are happily using Iceberg. So we are actually using in production with on-call SLAs and everything else. And we are happy for the moment. And we have a couple of use cases, but we are limited to 35 minutes. So we just choose one of them. So we also have CDC use cases, but we choose the largest one from the data volume point of view, which is an append-only system. So we have an easier life from some point of view, I mean maintenance operations. We have about 10 petabytes of data per table. We have a multiple cloud system. So in total, we have more than 30 petabytes. What's important, this is the amount of data after the Iceberg migration. My colleague Spandana will show you also the improvements. I mean, we saved a lot of petabytes. 1 petabyte, you know, it's 25,000 per month. So I think we got some savings with this movement. This system, it's powering the analytic query platform. So it's the second use case that I told you available to internal teams. And at the same time, it's used as a disaster and recovery system. In this case, which fortunately doesn't happen very often, we take data from the data lake and we replay it back to other systems in case they lost and they need to replace something. The next slide is going to handle the initial architecture that we built it. I think it was 5 or 6 years ago. The system that I'm showing. Basically, we were just learning how to build our data lake on our scaling challenges. I mean, even if we have experience, we didn't have experience with so much of data. Maybe some things are looking a little bit naive. This was, again, the first system. Briefly, what we have here. We have the Kafka clusters, and I'm going into details in the next slides. And we have a custom streaming system, which was producing data with a partitioning scheme using, probably you know some of them, the so-called Hadoop sequence files, which were stored in S3 storage. And after that, we have a bunch of systems, one of them being Hive Ingestion, that consume this sequence files data and transform them to Parquet, use Hive as a catalog, and we have Spark SQL and Trino in order to read them. And you also see in this diagram another two components. One is the exporter that I previously mentioned. We have to send this data also to our external customers, and the disaster and recovery system. What's not into this diagram, there are another system. For example, we had notification system when the streaming system was creating a batch data. We have some MySQL databases. This is a high overview. This system worked until it didn't work. What were the challenges? Probably some of them are common, and we try to do some work around. For example, we try to build our own naive metadata files on top of our data, kind of probably Iceberg version 0001, in order to mitigate some of them, but it didn't make sense basically to rebuild something which probably was built better. The challenges was the classic list approach, which kind of works in S3, I mean, even on a large scale, but it's extremely expensive. But it doesn't work at all in case you want to maybe use as an alternative compatible S3 systems. Latency was a little bit bigger, so it was about 1 hour. We also had unwanted amount of complexity from our custom streaming system. We miss a compaction service. We try to create file as large as possible from the ingestion, so we were always on the edge, out of memory errors versus creating files good in size. Data layout was not optimal. Query performance was again suboptimal. We tried to mitigate some of these issues, throwing money until it didn't work even like that. And we knew it was a time to do a big change. The big change was moving to Iceberg. As I wrote, it wasn't an option. We had to move to a table format or shut down what we had. We also started to get, the initial system managed successfully to fill in business use cases, so people started to come up with more things. So they ask also for CDC use cases where you have updates, deletes, these are not native supported in Parquet files. So again, we need something on top of them. And we started to explore the main ones, Delta Lake, Hoodie, and Iceberg. All of them look promising, and this is, to me, it looked like, the decision to choose Iceberg, it took us some time to go with it. All the three table formats, to me, all of them look really well. All of them have very strong supporters. I mean, people who know what they are doing, and they have decent communities. And it was extremely hard to build our own benchmarks in all three of them in order to be sure, yes, this is what we want. So in the end, we choose Iceberg because of a combination between strong community support. I mean, we have seen that people are answering quite fast on forums or on Slack. And also, Tabular team was extremely supportive. I mean, they actually try to understand our use cases. So this is the main reason. I think we choose well. We don't have, how to say, technical arguments against data lake or Hoodie. It's just what we decided to use and to go on. How is the new architecture? Again, a very high level point of view. So we have the Kafka clusters, and I'm going to details in the next slides. We have the ingestion, which is based on Spark and AWS EMR. We write all of our data, so all the trillion of events, to a stage table. And after that, from this stage table, we build derived table per use cases. How we build them, we have two approaches. One, maybe a classic approach. Hourly, we run some big queries extracting what we need. What we would like to use as soon as possible is to use the streaming ability from Iceberg for a bunch of reasons. One, we'll have the derived tables built with a very low latency, so we should have them in less than 10 minutes up and with the proper data. Second, we'll be able to save some money. With that, I mean, we'll not launch so many queries against the stage table. We still use Hive catalog. We don't have a good reason. I mean, the only reason is that we didn't have time to look into something else. But I would love to look into better replacements. Again, in order to look into data, we use both Spark SQL and Trino, and Pandana will give you more details. And you see there are MySQL too, and I'm going to talk about it in the next slides. The next slides are going to handle the core technical aspects. I mean, Kafka ingestion, data processing, and after that, the maintenance stuff. On the ingestion side, we have a situation which I haven't met it in other companies. We have so much data that we were not able to have only one Kafka cluster, and the Kafka cluster which always work like a breeze. So we have, right now, we have 12 Kafka clusters. We have a group of Kafka clusters, but this is going to increase in future. And this has a bunch of challenges. I mean, you don't want to have basically an ingestion per each cluster because you will have too many tiny files, or you will have too many concurrent writes against the Iceberg table, which might have some performance impact. I mean, the commits will have to be retried. On top of that, we were asked to build our ingestion resilient. What does it mean? We should be able to ingest data with minimum impact. Also, when a cluster group is not working, or just a cluster from a cluster group, or even a particular topic. I mean, you can have a topic with, let's say, 1,000 partition, 900 are working well, 100 are working not so well, and you don't have to be impacted. And we figure out, I mean, we try to use all the streaming systems that we found on the market, and in the end, we had to build our own ingestion, which is based on Spark, and it's doing its job. We didn't have time to make it open source. This is something that would be interesting to do it in future. in case that other companies have our challenges. And like that, we were able to keep the ingestion in decent parameters. So we don't create too many files. And again, we work good enough even when our cluster are not entirely in a good shape. After you read the data from Kafka comes another interesting problem. You have to usually to do some transformation and write it in Iceberg in using some partition that you choose. On the right side, you see our partitioning scheme. So it's based on dates until the hour, and after that we have some hidden partitioning from customer ID and event type. So we have probably about thousands of event types. We weren't able to use them as classic partitions. And we also had to do a lot of transformation. So it wasn't just reading from Kafka, convert from protobuf to Parquet, and just write the partition data. We have some complex processing in some cases. We have to even to use some native libraries. So native libraries built in C by other teams outside of our control. So we have skew issues from both processing and distribution. That's why Spark Adaptive Query wasn't the best for us. It works somehow, but we still had skew because of data processing. Why? Spark Adaptive Query execution is trying to split your partition based on data size. So it should handle the skew related to data size distribution. However, it's not able to take into account our event processing, the fact that processing 100 megabytes of event of types X are way more time consuming than of event type Y. Or to make it harder, you can also put our customers into the same table. So as I wrote, it worked somehow, but it impacted data latency, and it was more expensive than it would have been. The biggest impact was on backfilling. When you have to do a backfill of 2 hours, for example, I will show you some production data to understand the data size. So what was the solution? We wrote our own custom Spark partitioner, and I don't have the time to enter into detail. If somebody is interested, we can discuss on email. What I added the method signature, where you can see it's in Java, basically the main parameters that you can have. You can specify your partition capacity. This has to be computed, take into account what kind of machines are using, how much memory do you have per executor. And the most interesting things are some cost function. So we can declare a cost function per event type, or it can be defined on key level. I mean, as I told you, some customers have transformation which are taking more time. And basically that's all. The partitioner, it's making sure that data is evenly distributed. Of course, if you build the cost function properly. And like that, we were able to use distribution none. The partitioner is also sorting the data. So we got way better results compared with adaptive Spark execution and distribution hash. Some data from production. This is we have 4 production clusters right now. This is some data from the largest cluster. As you can see, if you take a look on the average, we write about, let's say, close to 4 gigabytes per second, and the maximum rate that we reached during this interval was 12 gigabytes per second. Maximum added record is 76 million per second. When adding files, we have in general about 150 as a M1 array per second. And the last one, the last slide shows, we call it executor load. We don't want to waste money. I mean, we want to have our Spark cluster working fully. So basically, here you can see that the 2-hour average is 70%. So it means that skew is in a good shape. I mean, we don't have unused executor slots. Some things that help us, and I thought is going to be interesting maybe also for other people. The first one, we increase the multi-part size bytes. Why? We write, as you have seen, a lot of data. So a couple of hundred files per second. It was important to minimize the number of put operation. Even from a cost perspective, 1 billion puts, I think, are costing about 5,000 per month in S3. Put 10 million, put 1 year, and it's a lot of money besides performance. The second one, of course, this makes sense if your ingestion is optimized enough in order to produce file with this size. The second one is a delete batch size. Using the default value, we had too many reduced request rates from S3, and this was the only solution that we found. And the last ones are related to compression. In our case, this standard was the best choice, and I think is the best standard for everyone, but maybe somebody has a counter example. And we use different ingestion levels. So for ingestion, we use level 1. For compaction, we use level 7. With level 7, we save about 15%. 15% is a lot when you have tens of petabytes. Last point, data layout matters, so try to find the best sorting column order for your data in order, again, to, if your data layout is data which looks the same, stays the same, the compression algorithms look way better. With that, I will leave the presenting to my colleague Spandana. Spandana?
Yes, thank you, Cornel. So yeah, next slide. So on once the ingestion is over, we have our orchestration around how do we maintain all our Iceberg tables. So for maintenance, we have implemented lightweight Spark applications to handle maintenance across all our Iceberg tables. So we currently have a cron job set up that would trigger our Spark application to handle our maintenance jobs on a timely manner. So our ingestion is a streaming application with a small batch size of 3 minutes. So we do generate multiple small files. So the first maintenance job we run is to compact our data files every hour. We have I'll go into more details about how our hourly compaction job works, but we have a compaction job, maintenance job that runs every hour. And then we have our expire snapshots job as well that runs hourly. In the current use case that we are discussing, we don't require time travel. And so that's why we run this expired snapshots hourly so that we get rid of the older snapshots. And also we save the storage costs from all the expired smaller data files that were left back from compaction. So these are the hourly hourly maintenance jobs that we run. We have daily maintenance jobs like the remove orphan files, and we also run rewrite metadata files, which is the compaction of the metadata files every day. We also included the delete data operation as part of our daily maintenance. This is just to clean up data to comply with the GDPR use cases that we have. So yeah, Cornel, can you go to the next slide? Yeah. Looking a little closer into our compaction job, so we had to add hourly partitioning to our table, mainly to accommodate data compaction. So we run compaction on the previous hour once the ingestion has completed for that hour. This ensures that we can get delivered the best query performance to our downstream services as soon as with max 1 hour latency. The data is available for query within less than 10 minutes, but once the compaction is done, we do see significant improvements on the query side as well. So with data compaction, we are seeing about 30% reduction in our file sizes on the final staging table that we have in S3. So on the compaction job, we have also configured the job to apply sorting on some of our high cardinality columns, which we use in a lot of our query filters as well. So the sorting has helped both in improving the query performance whenever we apply filters on those columns, and also it helped us in some cost savings because sorting has provided better compression ratio, especially on files having those columns. One major difference where we have seen is we do have some downstream ETL queries which heavily query on those some of those sorted columns, and in those ETL pipeline outputs, we have seen up to 50% reduction in the overall data set size when compared to what we had with our Hive setup. So that is a significant change in the data set size. So next, I would like to talk a little bit about the impact we have seen with this moving to Iceberg on our query side and also on the cost savings. So on the query side, we are currently using Spark and Trino as our backend query engines. We mostly use Spark for our ETL pipelines. We have data scientists using notebook queries backed by Spark, and we have scheduled hourly and daily jobs running on our Spark clusters. And as Cardinal mentioned in our architecture diagram earlier, we do generate a lot of derived tables, materialized views, which are then used for subsequent analytical queries by other internal teams. So all these are are run on our Spark clusters. And we use Trino mainly for ad hoc querying purposes, interactive queries, and we have set up superset integration to our Trino clusters. Superset is a plain UI interface that it provides on top of any of our query engines. So we have a lot of analysts running ad hoc queries and building dashboards powered by our Trino clusters. So we also, as part of this moving from Hive to Iceberg, we also moved to Trino relatively recently. Before Trino, we were on Presto, but with Trino, we have seen 25% improvement in our query performance. So currently, all our production systems are moved from Presto to Trino. So we have Spark and Trino running on Iceberg. Overall, just with the Iceberg changes, we are seeing close to 2 to 20 times better and faster query performance compared to what we had in our previous architecture. And I think all our end users are quite happy with the faster queries that they are getting. On the cost saving side, I just wanted to mention what are the main factors that helped us. On the ingestion side, ingestion and the maintenance side, it's mainly the compaction and the sorting job. As I already mentioned, sorting has enabled much better compression ratios, and the file sizes are much smaller. So that has helped us save a lot of our S3 storage costs. And on the query platform side, with the faster queries, we have less compute time. Our query clusters are up. The uptime of our query clusters has gone down. We have auto scaling enabled as well. And on the S3 API calls, we are seeing much fewer S3 API calls compared to what we had on Hive. So Cardinal, do you want to go to the next slide? We have some metrics there. Yeah. So if you can see here, from Hive to Iceberg, we are seeing 10x reduction in our S3 GET calls whenever we run our similar queries pipelines that we have. And also our S3 list calls have gone down by 25 times. So that shows significant cost savings on the S3 API calls. So what's next? At Crowdstrike, we are still working on onboarding many of our other use cases onto using Iceberg ingestion. So the current challenges we have is how do we scale our maintenance orchestration setup that we have as we add tens of more tables, and eventually maybe by the end of year it will be close to hundreds of tables. So that's a current challenge we are working on because we sometimes still see intermittent failures in our maintenance jobs as our data volume on a table increases. As we mentioned, currently we have up to like 10 petabytes of data on some tables, and that's ever increasing. So we do get hit into some issues, which we are trying to fine tune and figure out what configuration works in the long term. And though we didn't get to discuss, we do have some CDC use cases running in production, and there are some challenges over there, especially around how do we avoid concurrent commits when both ingestion and compaction are writing simultaneously on the same partition. We are working on some of those challenges. And coming to the future scope, as I said, we are working on multiple use cases, a lot of CDC use cases where we are trying to onboard a lot of our graph analytic data into Iceberg. And also on the existing systems, we plan to leverage the schema evolution feature that Iceberg provides and use that to update our partitioning schema and make sure there is still that 10-15% of use cases where it's still not as performant or as fast as we would like it to be. So that's where we are trying to evolve our schema to help improve those small 15% use cases as well. And also, as Connor mentioned, this scale at which we are operating on some of our data sets, it requires us to have our in-house Iceberg features that we develop to handle our use case and scale. So we are working on some of those changes, which I think eventually, as we also learn more through our experience, we plan to contribute to the open source Iceberg community. And then we are hiring, so definitely check out our careers page, and we are actively always looking for strong candidates with experience in Spark, distributed systems, different file formats, and it's great if you have Iceberg experience. So that's all. Thank you for attending the session, and we are open for questions.
Okay, thank you, Cornell, Spandana. That was fantastic. There's a number of questions here. I'm not going to go in order, and I'll try and group things together that are similar. The first ones are related to the ingestion side. And you mentioned a little bit as future work, but handling schema evolution, especially from stream ingestion and into Iceberg tables. Are you doing anything interesting there, some sort of schema registry, or is that a challenge you've had to solve yet?
Not yet. Our main challenge that we have right now, it's the number of resources or engineers or people, as you want to say. So as I mentioned, Crowdstrike was very successful. It's extremely hard to deal with the growth pains. So we did what was a must in order to fulfill the business needs. That's why we still use Hive. We would love to go into more things. That's why we have the last slide which we are hiring. For the moment, there's a current situation.
Looks like lots of fun problems to work on. So yeah, look into that if you're interested in working on cool Iceberg problems. Related to also ingestion was, you mentioned the use of MySQL to sort of coordinate the checkpointing, and you get multiple clusters and you're writing to Iceberg. And maybe just talk a little bit, maybe one layer deeper there on the architecture and some of maybe like the hardest problems you were solving. That's a very difficult distributed systems problem.
The main issue, as I mentioned, take, for example, Spark structure streaming. Connect Spark structure streaming to a cluster Kafka, which is almost working, which means 3 partitions are extremely slow. The other ones are working well. If you read in the documentation, the idea is try to isolate them somehow. because otherwise you'll have to wait for the slowest one in order for your job to finish. And on top of it, add a bunch of Kafka clusters that had to be united together, and at some moment they can go in maintenance mode. Your ingestion code should be aware of that. Previously, in other companies, we didn't have these challenges. So what we had to write our own Kafka code, our own Spark Kafka integration, which is launching multiple jobs in parallel, and is able to handle, for example, the so-called quarantine partitions which are not in a good shape, or clusters which are not in a good shape. So it's a lot of code. I can't say it's, it's extremely complex. Maybe we didn't invent anything, but you have to take care of all the unhappy cases that can happen. So basically, we start a job reading from Kafka. We don't wait for the slowest partition to finish, even if we have the maximum of offset at some value. We stop after a timeout that we have. We persist these things in MySQL using the offset match that we have. Why? Because you might have a system restart. So you have to know where to restart, what to do. It might sound a little bit like over-engineered, but believe me, we would love to just use Kafka Connect, Flink, Iceberg streaming, and work as a breeze.
Yeah. I think the open source community looks forward to any contributions in this space. Those are tough problems to solve. So
the other, maybe also, as we said, we have a lot of data, so we also try to be cost effective. If you don't care so much about skew, okay, if you have some slow partitions, just wait for them, but you will have 8,000 cores doing nothing, waiting for your read to finish. So, and this is a lot of money, so we should make happy our stakeholders.
Yeah, AWS appreciates it. All right, a bunch of questions related to, switching gears a little bit, I think, Spandana, maybe towards you, the trade-offs around compaction and sorting. So sorting, you get better compression, you get better query performance, but obviously there's a cost to sorting when you're doing compaction. And there's just general cost of running all the compaction jobs. So there's a lot of savings to be had, but there is cost involved with doing compaction and sorting. So can you just walk us through how you all think about those trade-offs?
Sure. I don't have the exact numbers, I don't have that prepared, but maybe we can have that conversation later. But sorting, yes, we understand there can be a overhead of the cost we pay for as you sort around compaction. So we have tried to shortlist that only to our top 3. We have hundreds of fields on our table. So we try to bring it down to top 3 fields, which are heavily used in our query filters, and that's what and they are also in line with our partitioning schema. So that's how we could come up with the balance, and we did do some benchmarking, and for us with the sorting fields that we have picked, it is we are still benefiting with the cost savings we get despite having a separate job which runs all this.
Perfect, that makes sense.
I would add a very short thing. So here, I think each use case is different. Maybe for another company where you don't have to store data for 3 months like you do, maybe you would love to save more money by having a lighter compaction. In our case, it makes sense, for example, to use this standard level 7, even if we have more CPUs, because again, the storage is a main cost. But for other companies, it might not be that. So I think the most important thing is don't take anything for granted and try to think at your use case and do this comparison. What do I save from that? What do I lose on this side?
Agreed. All right, well, we're actually at the end of time, so there are many more questions. As they mentioned at the top, if your question didn't get answered, they shared their contact information. You can send them emails directly, and they will get answers to your questions. It's a fantastic topic, lots of good stuff to cover there, and I'm sure more to uncover as people have deeper questions.